Swayam Prabha. Digital India. Educated India.
Today, I am going to talk about another nano finishing process that is known as magnetorheological finishing MRF. Current status of related finishing technologies. Now, here MRF process is described in terms of two very interesting figures. Now, on the right side if you see, you have two magnets indicated by N and S, north pole and south pole, and there is a lens which is to be finished. Now, there is a circular channel in which you have a MR polishing fluid which is shown here by the blue color, and you can see that this channel is continuously rotating in which the MR fluid is there, and here is the lens which can rotate at its own axis and it can be tilted on either side to cover the whole surface of the lens for finishing purposes. Now, when this MR polishing fluid comes under the influence of magnetic field, it gets stiffened, and once it gets stiffened, the abrasive particles which are part of the MR fluid, they come and finish the lens. Now, if you see on the right side, here is the MR fluid and arrow indicates the direction of movement of the MR fluid, which consists of abrasive particles also. Now, the white layer here shown is that of abrasive particles mixed in the MR fluid, because iron particles or ferromagnetic particles which are there in the MR fluid, they will get attracted towards the bottom of this channel, that where magnetic field gradient is very high compared to at the top surface. So, most of the abrasive particles will come on the top surface and they will interact with the surface of the lens which is to be finished or named as workpiece also here. Now, because once these abrasive particles come in contact with the lens, then two types of forces are again acting as I mentioned earlier. One is the normal force which is responsible for the penetration of the abrasive particle into the lens. Now, when I say normal force, this is the normal to the surface of the lens, and there is a axial force or tangential force which is responsible for removal of the material from the lens. Now, since irregularities of the lens can be represented as the peaks of the triangular shape. So, depending upon the depth of the penetration and axial force or the cutting force applied due to the rotation of this channel where MR fluid is there, that will remove the material in the form of the micro or nano chips. Whether it is microchip or nano chip will depend upon the abrasive size, the force that is acting on the abrasive particle, and that is transferred to the lens or the workpiece, and available tangential force for removal of the material in the form of the micro or nano chips. Now, this was developed initially by at the University of Rochester, USA, and they developed a machine. That machine is known as QED machine, which is very expensive. It may cost more than, it cost about 2 to 3 crores of rupees, and it is very effective in finishing the objects like hemispherical like or semi-spherical lenses, etc. Key features of this process are very high precision finishing of lenses, spherical, flat or aspherical lenses are there. surface finish that has been obtained is lowest one is 8 angstrom, that is 0.8 nanometer Ra value, and process is deterministic, because here with the help of the electromagnet that are shown here by N and S, you can control the magnetic field, or in other words you can control the normal force that is acting on the abrasive particle to penetrate the workpiece. That is why it becomes more of the deterministic in nature as compared to the abrasive flow finishing process, where that determinism is not there in the process. That is why this MRF process and abrasive flow finishing process both were combined, and we developed a process called magnetorheological abrasive flow finishing process. There are certain limitations of this particular process. First is the shape limitation. Only certain shapes can be finished by this particular process because of the configuration of the setup. Standard MR polishing fluid is ineffective for polishing hard materials. Now, a setup has been developed at IIT Kanpur, and that is CNC computer numerical control magnetorheological finishing process setup. You can see this particular area within the circle, where we have attached an attachment which consists of rotating wheel made up of perspex material. Inside this there are the magnets which you can see here, and here is the place for the workpiece to be placed. This can be metallic, it can be non metallic. When this wheel rotates, which is having a layer of the MR polishing fluid in the form of the ribbon, which is shown here by the arrow, and once it rotates and you feed the workpiece inside the rotating wheel, the same situation arises which was shown in the earlier slide. That means, the extrusion of the lenses starts taking place, as you can see over here, that those abrasive particle in contact with the lens, and extrusion of the fluid is taking place. As a result of that, this finishing of the lens takes place. In the same way, here finishing of the workpiece that you place here, flat workpiece in this particular case will take place, and we mainly finished the silicon wafers over here. You can see the enlarged view of this particular one, 5 is the workpiece, and this is the enlarged view of the ribbon that is over here, and you can see the effect of the magnetic field which is forming the chains of the iron particles in between the chains. You will see, if you further enlarge this, you will find that abrasive particles are entangled between the chains, or even in some cases within the chains, and when these abrasive particles come in contact with the workpiece over here designated as 5, interaction takes place and material removed in the form of micro nano chips. You can see in this setup CNC milling machine is there, and 2 is the AC motor with speed control over here, and 3 is the chain drive that you can see, and 4th is a permanent magnet assembly which is on the rotating wheel, 5 is the workpiece, and 6 is the workpiece fixture, and 7 closed view of the ribbon, as you can see here. Now, this shows the finite element analysis of distribution and direction of magnetic flux density on and around the magnet. Permanent magnet are used, you can see over here, and you can clearly see the areas where very large magnetic field is there and comparatively small magnetic field is there, and this analysis had been quite useful in developing this particular process. Now, mechanism of material removal in case of magnetorheological finishing process is important to understand. We have the CIP, that is carbonyl iron particles, form a chain like columnar structure with the application of magnetic field, and these CIPs and abrasive particles they get, rather CIPs get aligned along the lines of magnetic force, and the abrasive particles get entangled within the chain or between the chains. The magnetic force between iron particles provides bonding strength to it. Now, you can see here these yellow this blue colors are the abrasive particles, and they are these purple colors are the abrasive particles, and others are the iron particles, and abrasive particles are coming at the top, which are interacting with the lens, as you can see here. So, abrasive particles are responsible for the removal of the material from the lens. Now, when these chains have relative motion with respect to the workpiece, here workpiece is the lens shown in this blue color, workpiece surface, the asperities on the surface are abraded due to the shearing or plastic deformation at the tips. Now, this figure clearly more clearly shows the mechanism of material removal. As you can see here, magnetic field direction is shown with this arrow, and this is the fluid flow direction, and these are the abrasive particles yellow color over here, and because of this normal force, this abrasive particle is penetrating inside the workpiece surface, and there is a shearing force which is responsible for removal of the material in the form of the microchips or nanochips, depending upon the depth of penetration. Now, I will show you some of the results that we have obtained using this particular process. You can clearly see this is the rough part or initial part which was taken for finishing purposes. This is the finished part, and you can see the reflection of this pen tip reflection over here, shown over here. So, that simply means this is a mirror finish that has been achieved during this process. Initial surface roughness was 1260 nanometer, and final surface roughness that achieved was 14 nanometer. So, there is substantial improvement, say around 100 times reduction in the surface roughness value. Workpiece was silicon blank, 50.6 millimeter diameter, wheel speed was 200 rpm, working gap was 1 millimeter, and table speed to cover the whole surface was 20 millimeter per minute, and total finishing time is quite large, that is 3 hours, and MR fluid consists of CIP carbonyl iron particles, cerium oxide as the abrasive particles, soft abrasive particles, water and glycerol were the other fluid that were used over there, and this is the surf analyzer plot for the rough surface or initial surface, and you can see that 1260 nanometer is the initial surface, and quite large peaks and valleys are visible in this particular surface. After finishing, again we took the surf analyzer plots for this particular finished workpiece, and you can clearly see the difference in the left side figure and the right side figure. Right side figure is more or less just a straight line giving the surface roughness, average surface roughness as 14 nanometer. So, this clearly indicates that this process is very effective for finishing silicon type of the workpieces. Here water is used, which chemically reacts with the silicon and develops or produces a top surface oxide surface, which is removed by the abrasive particles as well as to some extent by the iron particles, because it becomes quite soft after chemical reaction. Now, this is the atomic force micrograph of the initial rough surface, for which the surface roughness value reported in the earlier slide was 1260 nanometer, and this is I have already shown you, and this is the finished surface of the same blank after finishing by MRF process, and in this particular case the surface finish obtained was 40 or 12 nanometer. As you can see, in this case it was 12 nanometer. Now, at IIT Kanpur, BTech students developed a similar kind of the setup, and they conducted the experiments, and they took the lenses which are used for wearing on the faces of faces, and the initial surface roughness that we obtained was 53 nanometer. Then they finished it for 50 minutes, and after 50 minutes they found that the surface roughness obtained was just 11 nanometer. So, there was a substantial reduction in the RMS value of the surface finish, that was around 5 times in 50 minutes, and 11 nanometer is really a very good surface finish, provided there are no defects. And since here the forces acting on the component are very low, which are deterministic. So, those kind of the things can be, or damage or defects in the finish length can be minimized. Now, there are certain problems associated with magnetorheological finishing process. First thing is the shape limitation. You have seen that you cannot finish different kind of the shapes, complex shapes cannot be finished, 3 dimensional components cannot be finished. A small finishing spot is formed over there. I have not discussed finishing spot, but a small area is being finished at a time. That is why it takes lot of time. As you have seen, I mentioned there that finishing of silicon blank of 50.6 millimeter diameter took 3 hours, which is a substantial time, because of this particular region that finishing spot is small. So, the total area covered is very small, and it takes longer time for finishing the whole blank. Standard MR polishing fluid are ineffective for polishing hard metals, because those fluids are those abrasive particles like cerium oxide are soft. So, what we did, we combined the two processes, MRF process and AFM process, and named it as magnetorheological abrasive flow finishing process, to overcome the weaknesses of this process as well as the weaknesses of abrasive flow finishing process. As I will explain you, AFM and MRF. MRF is not suitable for hard materials, AFM is externally non controllable. We combined these two and developed the process as magnetorheological abrasive flow finishing. The viscosity of abrasive medium in MRF process can be manipulated and controlled in real time. Hence, it helps in deterministically and selectively abrading the workpiece surface. Two important points are here, that you can manipulate it and you can manipulate it in real time. So, you can finish it in a definite desired fashion. The use of machining setup similar to abrasive flow machining will remove the shape limitation on workpiece surface to be finished, and this is what we have really done. What we did, to understand the mechanism of removal of material during MRF process, we took a photograph of the MR polishing fluid in the absence of the magnetic field, and you can clearly see the iron particles and abrasive particles are randomly distributed in this particular figure. Now, then we took the another figure, and here the figure was taken on the application of the magnetic field. That means, electromagnet was supplied the current, magnetic field came into picture, and you can now clearly see the chains are being formed. They are quite visible over here. Iron particles formed the chain, and in between iron particles you can clearly see the large size abrasive particles are there. They have been taken deliberately large size to see in the microscope, so that we can understand what is really happening during MRF process. So, it clearly indicates that iron particles get aligned along the magnetic lines of force, and within the chains or between the chains iron particles are entangled. Now, when these iron abrasive particles are entangled, when these abrasive particles come in contact with the workpiece surface, they abrade the workpiece surface and remove the material in the form of the microchips. As you can see in a schematic diagram here, these are forming the chains along the magnetic lines of force, and in between the chains you can find the abrasive particles are there. When these abrasive particles come in contact with the workpiece surface, they remove the material in the form of micro or nano chips, and this whole medium is moving either in this direction or in this direction, depending upon whether the stroke is upward or downward. One cycle is completed when the medium moves up, comes back, goes down, and then returns to the original position. That completes the one cycle. Now, then what we did? We took the atomic force micrographs of the initial workpiece surfaces before finishing, and we measured its surface roughness. You can see this is atomic force micrograph, and this is the surf analyzer plots, and the initial surface finish was R A was 0.28 micrometer, R Q was 0.34 micrometer, and R Y was 1.95 micrometer. Then after finishing it for 2000 cycles with silicon carbide as the abrasive particles, not the cerium oxide, silicon carbide as the abrasive particles, which is hard, then the surface roughness value came down to 0.1 micron. So, there was 2.8 times reduction in the surface roughness value, and R Q also came down to 0.12 micrometer, and R Y also came down to 0.95 micrometer. That means, all the three characterization of the surface finish are improved, and you can see the difference. Now, after finishing, we are not very happy with the kind of the texture that we obtained on the surface, finished surface. Then what we did? We finished the component same way and the same component with the help of the diamond particles of the same size, and we did not get improvement as long as R A value was concerned, although R Y reduced to some extent and R Q remains more or less the same, but there was a significant change in qualitative change in the texture of the surface, as you can see at the extreme right, and in the middle the R A value remains the same, but surface texture qualitatively surface finish has changed substantially. So, that tells clearly that there is the difference in the surface texture when you are using different kind of the abrasive particle. Problems associated with IMRAF process, magnetorheological abrasive flow finishing process. It is difficult to provide uniform magnetic field in the finishing zone due to fixed coils at two diametrically opposite sides of the cylindrical workpiece, which is fixed. Secondly, non-uniform finishing of cylindrical workpiece at different points across the diameter, since magnetic field is different at different points. That is why non-uniform finishing takes place of the cylindrical workpieces. So, to overcome these problems, we modified this particular process. We thought what should be the solution. So, what we did, that we modified this magnetorheological abrasive flow finishing process as rotary magnetorheological abrasive flow finishing process, as I will show you in the following slide. Now, you can see here on the left side, rest of the setup remains the same as I discussed earlier, but here is the set of the magnets, and these magnets are fixed in a fixture, and that fixture is rotated with the help of the AC motor. There is a chain drive, and this fixture is having the teeth, so which is connected to the chain drive, and as depending upon the RPM of this spindle of the motor, you will be able to rotate it, the magnet, and that makes a lot of difference in the finishing characteristics. Now, the enlarged view, what we developed was like this. These are the 4 magnets, and this is the type of the workpiece, and rest of are just the fixture to hold the magnet. You can hold the 4 magnets over in these 4 slots as given here, top and bottom. You can hold it, and then this whole fixture is rotated. So, extended view of the rotating the fixture, taper roller bearings were used. This is the bottom media fixture, and this is the top media fixture. and rest of the things are just for getting an appropriate RPM or rotational speed of the magnet. So, here make one point very clear that we are rotating the magnet, not the medium, but since magnet is rotating. So, media also will be rotating, and that rotating medium will come in contact with the workpiece, which is stationary, which is not rotating. So, the movement of an abrasive particle which was earlier moving in axial direction will be spiral directional movement of the abrasive particle, which will make lot of difference, and that spiral movement of the abrasive particle can be simulated with honing operation, where abrasive particle is rotating in the axial direction as well as circular direction. So, it is very similar, and similar kind of the cross hatch pattern is also obtained after RMRAF process. Now, there are various ways of putting the permanent magnets in the RMRAF process. One configuration is shown over here. You can have south poles opposite to each other and north pole opposite to each other. Now, you can see the distribution of the, this is the chains or the brush being formed by the MR fluid. Now, here you are putting south north and north south over here, and you can see the non uniformity of the brush being formed, because here there is nothing and here also nothing. Here in this particular case it is very uniform all around. Now, when you have only 2 magnets in place of 4 magnets, again there is the non uniformity in the brush being formed, and so it looks that this is a extreme left configuration is a better configuration as long as uniformity of the brush formation is concerned. If the brush is uniform, then definitely you will get more uniform surface improvement on the cylindrical internal or external surface. Then we also tried to take the magnetic field distribution, and you can see this particular case the field distribution, and here are the stainless steel workpiece which is kept here. These are the 4 magnets, and you can clearly see that in this particular case the field distribution is better than the other case. Now, so this configuration was adopted, which gave the better field distribution and more uniform distribution of the brush being formed. Same thing is shown here, and this arrow shows the rotation of the 4 magnets through the fixture in which these 4 magnets are mounted, and here this triangular filled symbol indicates the silicon carbide abrasive, and circular empty symbol indicates the CIP. And when these are rotating, then abrasive particle is moving in the axial direction as well as rotational. So, as you can see here that helical finishing path of polishing is opted by an abrasive particle. You can see the path, say this is the abrasive particle, then it will be moving like this and coming like this, and then only coming out over here following the helical path. And this helical path, when it is following, then the total length travelled by an abrasive particle before it enters into the workpiece and after it comes out of the workpiece zone will be much larger than when it is moving only in the axial direction. And if it is its path length travelled increases, then interaction also will increase with the peaks of the workpiece surface. As a result, higher or larger number of peaks will be sheared by that particular abrasive particle, or in other words finishing rate will increase in case of RMRAF process as compared to simple MRAF process, and that is the main advantage of giving rotation to the magnets as compared to the stationary magnets in case of MRAP process. Advantages of RMRAP process are indentation on the abrasive grain is due to combined effect of normal component of magnetic force and centrifugal force due to the rotation of the medium. So, these two forces are combining together and leading to higher depth of penetration compared to the MRAP process. Now, due to medium rotation and reciprocation, the cutting force is the resultant of tangential cutting force and axial cutting force. So, total cutting force also increases. Path followed by the active abrasive grains on the workpiece is non-linear, that is helical. It provides higher finishing rate as compared to simple MRAP process. You get uniformly finishes on the workpiece surface, and it is very similar to what you get in case of honing operation, and it generates H pattern, cross H pattern, which helps in oil retention in certain type of the workpieces. You can clearly see here the force diagram. This is for the MRAP process, and simple movement of the fluid is up and down as is indicated by the arrow over here. This is the north pole and this is the south pole, and here the normal force Fm is responsible for the penetration, and axial force, which is the resultant force, is responsible for removal of the material in the form of the microchips. It gives you the velocity diagram as well as the force diagram. But when you are providing the rotation to the magnet, or in other words rotation to the MR polishing fluid, then the force combination changes completely, and you can see here there is the radial force, there is the normal magnetic force, and there is the centrifugal force. All the three are acting in one particular direction, and all of them are responsible for penetration inside the workpiece surface of an abrasive particle. And a force normal to this, there is the axial force Fa that is acting due to the axial motion of the medium, and that motion is provided by the piston, and then there is a Ft tangential force and Fmt the component of the magnetic force in the tangential direction. Both of them are also contributing, and the resultant of these two forces Fa and Fmt and Ft, you get what is known as cutting force Fc, and this force is responsible for the removal of the material in the form of micro nylon chips. Now, this cutting force should be greater than the resistance being offered by the workpiece material for the removal of the material. Otherwise, the abrasive particle will remain sitting or implanted inside the workpiece surface. In that case, either a rotation of the abrasive particle will take place, so that it reduces its depth of penetration and shears off the material from the workpiece surface, or if it is pulled out, then it will leave the indentation mark or pit over there, and which will be nothing but the defect in the workpiece surface, which we really do not want. Now, you can determine different forces, magnetic force, you can determine radial force, you can determine centrifugal force, and then there is a frictional force, and there is a cutting force is the resultant of all the these three forces. Details are given in the research paper published by Mr. Manas Das. Now, we conduct comparison of magnetic field intensity. We conducted the experiments to find out the effect of rotational speed of the magnet at different RPM. As you can see the RPM of the magnet, and this is the change in Ra, and you can see in most of the cases there is some optimum RPM on which you are getting the maximum change in the change in Ra, and this is somewhere in the range of 50 to 70 RPM, and here is the workpiece stainless steel, then there is the EN8, and then there is a brass. So, it is found in this particular case that the change in R A is maximum in case of non-magnetic material and it is comparatively less in case of magnetic material, and it is more in case of softer material compared to the harder material like brass. Over here it is more compared to the harder material stainless steel. So, in this particular case you can see that in brass you have got substantial change in R A value why compared to stainless steel, which is comparatively hard for the same given time. Then we also try to analyze the magnetic field using fluid software, and you can clearly see the concentration of the magnetic field in certain cases in non-magnetic material like this, here more or less uniformly distributed, while in magnetic material it is concentrating in the area of magnetic material, that is the workpiece, compared to rest of the portion where it is less. So, you will not get uniform finishing, and also some of the magnetic particles may get attracted by so large force near the magnetic material that finishing rate will reduce substantially. Now, let us see some of the atomic force micrograph images of the surface modifying processes by RMRAP process. You can see here this is the ground workpiece surface where RA value was 0.27 micrometer, and this indicates the grinding ledge, and this is normal to this there was the MRAF direction or MRAF finishing lay. Now, and this is the surf analyzer graph. After MRAF process there was no rotation, simple MRAF process. This is the kind of the surface finish was obtained, that was 0.21 micrometer, but you can see the qualitative difference between the two, although there is not large difference in the RA value. Now, when rotation was provided say 60 rpm, the surface finish reduced to 0.10 micrometer, but there is a difference in the quality of the finished workpiece. First thing, we had here the grinding marks very close to each other, but much wider than the ground surface. So, this has improved, but in this case it has further improved. Some of the grinding marks have disappeared and finish is better, it has come down to 0.1 from 0.21 over here. Now, in case of brass, this was the case for stainless steel, which is quite hard, and in case of brass again we took a workpiece with 0.25 as the initial RA value, and these are the directions of the or ledge of the grinding, and MRAF will be definitely normal to this one, and at 0 rpm only simple MRAF process the surface finish was reduced to 0.17 micrometer, but with rotation and using RMRAP process at 60 rpm the surface finish was brought down to 50 nanometer, that is 0.05 micrometer, and you can clearly see the difference between this surface and the ground surface. So, there is a substantial improvement in the surface texture also after using RMRAP process on comparatively softer material like brass. So, it clearly indicates that there is a qualitative as well as quantitative improvement as long as nano finishing using RMRAP process is concerned. Now, surface roughness profile, you can see this is the initial surface profile after turning operation at 330 nanometer, and this is the final surface profile obtained of cylindrical workpiece at 16 nanometer. So, you can clearly see the substantial difference between 330 nanometer and 16 nanometer. We also try to find out of roundness measurement, because it is not only the surface finish of cylindrical workpiece which makes a difference, but out of roundness is also equally important, and in certain applications it becomes more important. So, we try to measure this, and initial out of roundness was 7.39 micrometer. Then after finishing we found that it reduced to 6.49. So, although there was not substantial improvement, there was a difference of 1 micron out of roundness, reduction by 1 micron out of roundness, but if this process is optimized for improving out of roundness, I am confident that this 6.49 will further substantially reduce. And internally finished cylindrical surface of stainless steel workpiece is visible over here. You can clearly see the reflections visible over there. So, these are the conditions which are given over there. The magnetic field was 0.66 Tesla, mesh size was 180 and RPM was 150, finishing cycles were 1200 and the pressure used was 40 bar. I will quickly go through a chemo-mechanical magnetorheological finishing process which was developed again at IIT Kanpur. It is a very good process for that particular purpose. Let us see some of the limitations of chemo-mechanical polishing process. It is not able to do planarization with constant finishing throughout the work surface except on circular work surfaces. It does not have flexibility regarding work surface, that is the shape and size. So, what we did that we combined the chemo-mechanical polishing process with magnetorheological finishing process and developed a process named as chemo-mechanical magnetorheological finishing process. Here magnetic field assists polishing pad instead of conventional polishing pad of chemo-mechanical polishing. Its flexible polishing pad removes the shape limitation on the workpiece surface. Because of this magnetic field it becomes deterministic also, you can control the forces. This is the experimental setup which was developed and you can clearly see that these are the VFD variable frequency drives, 2 variable frequency drive, and here the dial gauge to control the working gap between the top surface of the workpiece and bottom surface of the magnet. Now, this you can clearly see, here is the workpiece and this is the brush MR polishing fluid which is forming the brush, and this is the one which is really responsible for finishing. Now, initially there is a magnet actually which is, this is the top part which is shown, but if you see from the bottom then this top part and this part will be visible like this, and this is nothing but this particular part. So, here before really finishing start, this forms the brush as the brush shown over here, and when you rotate this magnet then this brush is responsible for removing the peaks from the workpiece surface and shearing off the peaks and improving the surface roughness. And when compacted MR fluid, that means you have compressed the pad, and then when it starts finishing, then you can see here MR fluid is here also, and it is distributed on all these surfaces. And schematically you can show it here that you have the north pole and south pole of the magnet. The iron particles or carbonyl iron particles or iron particles, they will get attracted towards the north pole because magnetic field intensity is higher. So, all the abrasive particles will be on the outer periphery of this particular brush, and here you are going to place the workpiece. So, in fact the abrasive particles will be in contact with the workpiece rather than the iron particles, and this is shown here. This is the MR fluid under specified working condition, and there is the base material in which you are forming this MR fluid, which is shown here by bluish color, and this is the particle, that is the iron particle, and gray color they show the abrasive particle. Now, you can see here MR polishing fluid without any magnetic field, all are randomly distributed, and when you apply the magnetic field you can see all iron particles are trying to run or move towards the north pole, and rest of the abrasive particles will try to remain on the outer periphery of the brush, as you can see clearly over here, because these are all iron particles which are moving towards, but here they are randomly distributed over the whole surface. Now, mechanism of finishing. The main use of MRP fluid is to chemical reaction with the silicon substrate to soften it. Now, chemicals in the MR fluid react with the surface material, that is the silicon material, forms the chemical compounds that can be removed by abrasive as well as magnetic particles, because that softened surface is very soft. So, even iron particles to some extent can remove that softened layer, and in aqueous solution, that is water solution, oxide forms hydroxyls that should be easily removed by magnetic or abrasive particles. Cerium oxide CEO2 becomes chemically active and soft abrasives to the silicon substrate, and it is used for ultra finishing. The mechanism can be explained in a simple way like this. Here you get the chains over there, and here are the abrasive particles. Say in fact, this is slightly different. So, chains are there. Now, this is the initial surface of the workpiece that we took it, then we polished it with silicon carbide 800 mesh size abrasive particles, oil based, where oil was the matrix material, and then we polished it with silicon carbide 400 mesh size abrasive particles, again oil based MRP fluid. So, you can clearly see the improvement, in the surface over here, and there is further improvement in this particular surface, but here you can see some defective marks over there which are really not acceptable when we are talking of nano or sub nano finishing. Then we polished it with the water based MRP fluid and cerium oxide as the abrasive particles, and you can see the difference, qualitative difference in this surface and in this particular surface. So, there was a substantial improvement, and we conducted this finishing in 4 different stages which are given in the research papers published in the CIRP in the year 2010. Now, you can see the initial Ra value was 1.21 micron, and afterwards we got the surface roughness as 0.01 micrometer. You can see the reflection of the surface, reflecting surface. We kept this IIT K bark DST written on a piece of paper, and we could clearly see the reflection of these words on the finished surface, and it is image of finished surface under sunlight also can be seen how well it is shining. Now, there is another, some books were kept, and you can clearly see the reflection of those books, or here is a metallic piece and its reflection can be shown over here. So, what I am trying to indicate that you get the polished mirror finish on these silicon workpieces using this particular process, and we were able to get surface roughness as good as 4.48 angstrom, which I showed to you in the beginning in the very first lecture of this nano finishing. So, that was a substantial reduction in the surface roughness Ra value from 1.26 micron, that is 1260 nanometer to approximately 0.5 nanometer. You can see here, I have tried to show here that initial surface roughness is 1.21 micrometer, RQ is this much, and final surface finish that we obtained, you can see here 4.8 angstrom, that is approximately 0.5 nanometer. This is the initial surface, this is the iron mesh size, this much we got it, and then we finished it to some extent, semi finished workpiece was there, and then fully finished workpiece there. Now, there were some defect in this particular case. So, one has to be careful in selecting the magnetic field. If penetration is too much, then and the abrasive particles gets pulled out, then such kind of the defects can be there. So, we should avoid taking very high magnetic field, otherwise such kind of defects may be there, which will lead to the rejection of the workpiece. And you can see 0.5 nanometer as the final surface finish that was obtained. So, conclusions from this particular section, that is on micro nano finishing, are as follows. Theory of cutting by abrasive particles is able to explain why surface roughness attains a critical value, especially in case of the processes like magnetorheological finishing, abrasive flow finishing or magnetorheological abrasive flow finishing processes, or MAF magnetic abrasive finishing process. Theory of particle rotation is able to explain the phenomena why increase in extrusion force does not improve surface finish and material removal rate in AFM process, MRF process and MRF process. Why one should have a slot in case of magnetic abrasive finishing process in the magnet, how many slots one should have and what are the advantages or disadvantages of having a slot, and why and when one should go for pulsed power supply in case of magnetic abrasive finishing, that was also explained in detail, and how the hybridization of abrasive flow finishing and magnetorheological finishing gave birth to MRF and RMRF process to enhance the process performance compared to individual processes, that is AFF and MRF process, or to some extent you can say even MRF process. The combination of chemo-mechanical polishing CMP and magnetorheological finishing MRF was done, and a new process called chemo-mechanical magnetorheological finishing process was developed, and it is able to give as good as 0.5 nanometer, that is 5 angstrom surface roughness value on silicon wafers. Thank you very much.